Good day! I'm Dr. T and welcome to my office. Today I'd like to discuss heat and temperature. In common parlance, the two are used pretty much as synonyms. However, they do represent two fundamentally different properties. Temperature, and albeit this definition is highly imperfect as there's a bit more going on, but it's definitely a good working definition. So, caveat over. Temperature is a description of the average kinetic energy of atoms and molecules. Atoms, molecules, everything is constantly vibrating. Nothing sits perfectly still. And of course, kinetic energy is the energy of motion. So where there's motion, you have kinetic energy. Obviously, in any system large enough, you're going to have some that are moving a little bit faster and some are moving a little bit slower. So we look at the average, and this correlates to temperature. As I mentioned in the aside, there's a little bit more going on, but not enough to worry about. Heat, on the other hand, is going to be the transfer of energy into or out of a system. A system is simply whatever we're talking about, and then everything else is called the surroundings. So heat is going to be the transfer of energy, specifically in a disorderly format. Typically, when the energy is being transferred in an orderly format, we call that work. So if you are pushing on a block and you're moving all of the atoms in the same direction, we would call that work. If you are warming up the block by getting all the atoms to just start bouncing around randomly, that would be heat. So heat is going to be the transfer of energy into a system. And of course, as one could expect, these two terms are going to be intimately linked. Temperature gets the abbreviation capital T for its variable, not to be confused with time, which is a lowercase t. Heat, for reasons that historians are still trying to figure out, has the symbol or the variable lowercase q. As I said, historians are trying to figure out why. Basically, it appeared in the scientific literature in, I believe it was the late 19th century, and it just stayed there, and no one really asked why. But heat is Q. Now, as I mentioned, system and surroundings. So the system, whatever you're talking about, so if I have an ice cube, the ice cube itself would be the system, and if I'm holding it, I would be part of the surroundings. Technically, literally everything is the surroundings, but usually we try and insulate things, so we're only really talking about a couple of systems. If heat is flowing from me into the ice cube, then the Q is going to have a positive value. So a positive Q means heat is going into something. Now, this has a couple of consequences. One, you might think, hey, this sounds familiar. Is that endothermic? Yes, it is. Endothermic systems have positive Q values. But it might be a little bit counterintuitive thinking of the Q as positive because we always tend to think of ourselves, let's just be honest. And so we would think, but it's cold, the heat is going out. Well, it's going out of you. Your Q would be negative. Its Q would be positive. So whenever you've got a system and surrounding, there's always going to be a sign change because it's flowing from one to another. Heat will typically flow from the hot thing to the cold thing. There's ways to get it to go otherwise, but you have to use work to do that. Okay, so let's actually set up some equations and look at this relationship between heat and temperature. So if I have a thing, and right now I'm going to be assuming that there is no change taking place other than the fact that the temperature is changing. If there's a change taking place, then I have to use different equations, and those I will discuss in another video. So heat is going to be Q, so Q is going to be set up equal to three properties. The first property is just simply how big is the substance. What's the mass? The bigger the frying pan, the more heat it's going to take to heat that thing up. This is why cast iron skillets take a while to warm up, but stay nice and hot once they do so, because there's just a lot of metal there. The next property is what we call specific heat. This is a property of all substances. It does change depending on the state the substance is in, as well as actually the temperature, because of course you didn't want things nice and simple, did you? And this is basically describing, well, in order to raise the temperature a specific amount, usually we say 1 degree, how much energy is taken per unit mass. So if I have water, the specific heat of water is 4.184 joules per gram degree Celsius. That means it takes 4.184 joules, our unit of energy, in order to heat 1 gram of water up 1 degree Celsius. If I want to heat it up 2 degrees Celsius, then I'm going to have to use twice the energy. If I want to heat up 2 grams of water, then I have to use twice the energy than I would have if I heated up 1 gram. And of course, as you can probably guess from that discussion, the last term in our equation is delta T, or the change in temperature. Delta is going to indicate final minus initial, so this is going to be shorthand for saying the final temperature minus the initial temperature. Because we are subtracting, you can actually use Kelvin or centigrade here, and that doesn't particularly matter as long as for the delta T you either use Kelvin or centigrade. And then once you subtract, you can actually divide and use a specific heat that has either of the two. Yeah, so this is my equation. So if I want to figure out how much energy it takes to heat my pot of water, then I would simply take the mass of the water in my pot, multiply it by the specific heat of water. They don't change too awful much with increasing temperature, but do be forewarned, if your delta T is huge, you may have to keep track of that, but that's something we usually leave to the engineers. So I take the mass of the water, I take the specific heat of the water, and I times it by the change in temperature that either I want or that I've received. And by solving for those, I can solve for the amount of energy. Obviously, this is algebra, so really, as long as I know any 3 of the 4 variables in that particular equation, I can solve for the other one. Now, to make things a little bit more interesting, of course, sometimes we're not just directly adding energy into something. Sometimes we have a hot thing next to a cold thing. The hot thing is heating up the cold thing, and the cold thing is allowing the hot thing to cool down. So in this case, we don't actually have a Q per se. Each one of them is going to have their own Q, but it happens to be the same number because the heat is going from one into the other. The only difference is going to be a sign change. So in this case, we reconfigure the equation so that it looks like the one I just described, but it's double. So I would have the mass of the hot thing times specific heat of the hot thing times delta T, the change in temperature of the hot thing, equals the mass of the cold thing times specific heat of the cold thing times the delta T of the cold thing. Now, because there is a sign change, at some point I do have to throw in a minus sign, so typically I just stick that at the end. So throw in a -1 just to make sure all the signs cancel out. And with this, you now have 6 properties. Solve for any one of them, assuming you know the other 5. To make life a little bit more interesting and or to allow you to solve for delta T is a little bit better, if in this scenario we are talking about a hot thing warming up a cold thing, then eventually their temperatures will equalize. Therefore, for your delta T's, remember that is temperature final minus temperature initial. The temperature final will actually be the same for both parties. And thus, you can do algebra solving for T initial or for T final, depending on which one you don't know. I will say, though, that solving for T final or one of the T initials is more difficult algebraically because there's a little bit more going on, so just be forewarned. So yeah, that is what we call the calorimetry equation. We call this calorimetry because we use calorimeters to help us measure things like specific heat or other properties that involve temperature. Calorimeters are basically just an insulated vessel for us to conduct our experiments in. Remember how I said the surroundings are literally everything? Well, it's hard to monitor the temperature change of literally everything. So what we want to do is isolate our system. So the system is isolated inside of our calorimeter, and thus we can control the surroundings very tightly and monitor their temperature change very closely. And the insulation is going to keep the heat more or less inside the calorimeter. Obviously, nothing's perfect, but we can do actually surprisingly really good with fairly basic insulation. So with that said, I'll see you in later videos and have a wonderful day.